more than 6 years, and this research actually we are doing for last, I think, 4 to 5 years. Well, I am just concentrating on today's presentation on the specific themes, that is hydration and the microstructure. Well, we know, all of us know, like when we talk about a concrete or any cementitious composites, we just talk about the mostly, we talk about the compressive strength. We just talk about the designate. So we talk about the 28 days compressive strength. But remember, now the cementitious composite, like I will say, has changed. Changed the. It has gone into a kind of a new dimension actually. That is, at the present is the addition of the final particles. We are keep on adding more and more of the final particles, and we are expecting the better performance. So when we talk about the performance, remember, as well as compressive strength, other things important is the hydration and the microstructure properties. And particularly when we talk about the finer size particles, rather than compressive strength, I would say the understanding on the hydration and microstructure properties is very much essential at this point of time. So I will talk about it in this way. Like, so first I will just let us go for some introduction, then some methodology, then resolution, discussion, and conclusions, and some of the references, some of the publications. Well, we all know what is a concrete. We know, like I'm changing the slides. I hope you all can see. Okay, like.
So yes, sir. It is visible, sir. Visible.
Okay, sir. Thank you. So now, what is a concrete? Do we know? Like the concrete is nothing but the addition of cement, aggregates, and some water. Now the point is, when we talk about the concrete, it is nothing but just the addition of the ingredients. So the key thing here is the hydration. The key thing here is the hydration. Now, what is my hydration? We all know the hydrated products that I get is the calcium silicate hydrates and the calcium hydroxide. Mostly, so there are many of the other things are there, but the primarily which are important among the hydration products are the calcium silicate hydrate and calcium hydroxide. Now, there are two pictures I have kept here. Okay, like one is, what is like the simplified equation of the hydration. Well, we know the calcium silicate, the tricalcium aluminates, dicalcium aluminates, means primarily the bogus compounds, when it comes in contact with water, they form the hydrated products. Primarily the calcium silicate hydrates and calcium hydroxide. Now the question is, well, suppose like you see, this is a like picture actually like given by some of the researchers. Now here are the cement grains, and the you can see that the cement grains are getting precipitated into the aggregates, or here it is sand particles, and this is actually ideally the hydration products, the hydrates. But it doesn't happen like this. You cannot get a system which is completely filled by the hydrated products, particularly for concrete. It is impossible actually. We know it very well. Okay, like we cannot get 100% hydrated products. We'll come to this picture actually. This picture, okay. There are some more clarity actually. Now you can see this is the cement particles in the mix before the hydration reaction. Means there is no water, only the cement particles. Now when I add water, what happens? The hydration starts. The hydration starts, and the hydration products keep some precipitating on the surface of cement particles. So means the process of hydration starts, and the moment they get the products, so they will keep on depositing onto the other cement particles, means the other unhydrated cement particles. And those cement particles again, okay, start going to hydrate. So that is the process actually is changed. Now, suppose ideally, if you see here, if we will see, we will assume the system is completely hydrated. Means you must be okay, like getting information like this color is the basically the cement particles, means the gray images, gray color, and slightly brownish color is basically the your hydration products. And this picture is showing the hydration products, the gray particles, the gray color of like particles, and also the white patches. White patches means that indicates it is having the system is having the hydration products, the unreacted cement particles, as well as there are some pores within the system. That is what we call is the porosity. So you can see it is inevitable. You cannot design a system or a cementitious system which will have no porosity at all. So definitely there will be some porosity. Now what is responsible? Who is responsible, okay, for the pores, the porosity? Basically remember is your how, okay, the hydration takes place. For example, we know there are permeable porosity, that is micro size porosity responsible of it because of formation of calcium hydroxide. Now what we are doing actually, over the time what we did, what researchers have done? Well, researchers have done integrating the pozzolanous, that is the pozzolanic materials, that is GGBS, pliers, or maybe silica fume, whatever it is. So why? To minimize the calcium hydroxide in the hydration products. So means for a civil engineer, we know I have least important on calcium hydroxide. I don't require. I require the calcium silicate hydrate, the one which is giving me all my required properties. It is giving me the better strength. It is giving me the impermeability. It is giving my the Young's modulus, everything. It minimizes the shrinkage. So all kind of properties I am getting from the calcium silicate hydrates. So, so we realize, we have understood, we have to minimize the calcium hydroxide. And we know the pozzolanic materials are mostly the siliceous. So what happens? These siliceous materials reacting with the calcium hydroxide and forms additional calcium silicate hydrates. And that additional calcium silicate hydrates is a kind of a bonus for me, which helps me in reducing the porosity, the pore size of the pore sizes, as well as it helps me in the impermeability, which is responsible for the durability of the structure, the sustainability of the structure, sustainability of the materials. So that's why the adding of photorunners are very much justified. Now, if you come to this picture, now understand. Now this is my test cylinder. My test cylinder is the order of 10 to the power minus 0, means it is in the meter scale actually. We know it very well. So the aggregates in the millimeter sizes, we know the clinker of it, but particularly the cement is in the micron size. Now, what is this actually? The moment you go beyond, now I'm getting the gel networks, the calcium silicate hydrogen colloids, the molecules. So means, so what I'm doing actually, these are my ingredients, and I am adding water, and the reaction is happening within this zone, the gel network, the calcium silicate hydrogen colloids, the molecular, reactions. But what is I am expecting? What is my performance? Well, I am expecting my performance in a meter scale. Well, what is the key here? The key is how you are manipulating, this zone, how you are understanding well about this particular zone, the gel network, the CSS colloids, the molecular reactions. And depending on this, how you are tailoring, you will get a performance in your test cylinder. That is the key actually, I'm telling you. That is the key at this point of time. Because I told you in the beginning, we are moving into the finer to fine materials, finer to fine particles. The moment you go to the finer to finer particles, understanding of it, this zone is very, very important. Now, what is the important? The hydration properties. The important is the microstructure properties. The important is the permeability properties. The important is the durability of it, characteristic. The important is the sustainability. So understanding this part is very, very important, and I am going to talk about that, how we are going to characterize that zone. So if you go to the history of concrete, we know 90s, we were started working on the normal concrete. Then we started from 5 MPa, very much lean, like mixes to about 45 MPa. Then 1960s, we know like most of the countries started becoming developed. By 80s, US, Europe, like Japan, or many countries got developed by using high strength concrete actually. Now, research is going on the nano based. So understanding the nano concrete is very much important at this era. So let me introduce what is a nano concrete. Well, I am defining, or we are defining, even the researchers are defining nano concrete as nano ingredients with at least one dimension of nanometer size. Well, let us go into the more in detail of the nanoparticles. Well, the nanoparticles is clustering of atoms and molecules are in the range of 1 to 100 nanometer. Well, we have a particle size distribution. Now, nanoscience is mostly in the cluster of 1 nanometer to 100 nanometer. But particularly for construction industry, it is very much challenging till now, going into the even 100 nanometer size. You must be knowing, till now, construction industry has not adopted the nanoscience, the nanotechnology, because of the problem in handling of this small size particles. Well, research is going on still, the more and more research is going on, and how we are going to adapt this technology into the construction. Now, the second is the economics. We will discuss about that at a later point of time. So, what are the advantages of this size particles? If you consider this size particles, what are the advantages? The advantage is the superior surface to volume ratio and excellent surface morphology. You have a higher specific surface area, and from morphological point of view, wonderfully excellent. And that is the two things which are the prime regions nanotechnology is getting more and more famous, more and more getting adapted in all of the fields, not only of it in the construction. So, for example, human hair is 5 orders of magnitude larger than nanometers. So, for understanding, actually, you can see our hair is 5 orders of magnitude larger than nanometers. Now, what is nanotechnology? I was talking about dealing with nanoparticles. That is one of its dimensions in nanometers. That is in 10 to the power minus 9. And a new era of technology utilizing the intensively small things leading to the extraordinary behavior in the properties of materials. So that is what is happening across the world, happening across the industries. So it is very much essential now for us to adapt it, but definitely we have to find a way how we are going to adapt it to it. Now, nanotechnology for concrete, well, if you see the research is not much new, but Indian point of view also it's not new. Many of the researchers have started working on nanoparticles, developing nanoparticles, working on nanoconcrete for a long back. So roughly you can say around 2000 where we started doing research on the nanoparticles or nanoconcrete. Now, this is a beautiful picture actually. I will talk about given by the Thomas et al. Well, now what they do actually? The nanotechnology ability to control or manipulate materials at the atomic scale level means now we are talking about the micron size particles, the reactions in the micron size. And suppose we go a little more, I will say the calcium silicate hydrates of an angstrom size, little beyond than the nanoparticle. But when you go about the nanotechnology, the manipulation can be done in the atomic scale. That is the key. How they improve? They improve the bulk properties, they improve the mechanical properties, durability and sustainability, and the volume stability. Even the lower level of environmental contamination. Because the structure is so much dense, so they are not giving any room for any kind of contamination, any kind of environmental interaction. So those are the few advantages I mentioned here. But if you see, there are numerous advantages when you talk about nanotechnology or the era of nanotechnology. Now, this picture is given by the Thomas et al. That is the seeding of a schematic. Now, this is basically picture from the modeling, from the modeling, and how this talk about Admixed promote cement hydration in the 4 volume to complement topochemical reaction cement surface. I will explain you what is this. Well, you know C3S very well actually. The C3S or CTS, but when you talk about the early age and all, let me consider the C3S. So what Thomas et al. Also considered the C3S. Now you can see water is already added, and this is basically a C3S cement particle, and you can see the once water is added, now water has completely covered this cement grain, or you can just C3S of it cement grain, C3S grain. So the red color indicates the hydration starting, the initiating. Okay, initiating. And this is the picture, okay, in the initiation stage, and this is the picture in the final stage. Final stage. Now, in the final stage, you can see here, these are the, well, the on the cement particles, you can see the size is reducing, simultaneously the red color. Red color means your hydration product. Okay, so size is reducing and the hydration products are increasing. Now you can see there are some, okay, white color patches that indicates the your porosity, or you can see the capillary porosity. Okay, I'm just stopping here 1 minute. So now the second picture now means A and B. Okay, you have understood now. Now come to the C and D. Well, C and D is same. This is same. Okay, your C3S. Remember C3S, but here we have added some nanoparticles. Now, after adding nanoparticles, or maybe okay, simultaneously, okay, we have added water. Now, what happens here? Actually, you can see same cement grain here. The hydration starts, means the hydration process started here. Now you can see here there are some additional cement grains are there, where the nanoparticles, means individual nanoparticles. You must have seen the dots. These dots are nothing but your nanoparticles. Nanoparticles means you have introduced a very fine size particle into the cementitious matrix. Now, what is happening actually? What is these small dots? The small circular dots? They are nothing but the calcium silicate hydrate seeds, which in the beginning itself, the nanoparticles started working as a calcium silicate hydrate seeds. That is what is happening to the nanoparticles. Now, to the right side picture, the D picture is, you can see the hydration is complete. Let us assume the hydration is complete. You can see there are unreacted cement grains as the previous picture, but you can see all the white areas, the white patches are now covered with the hydration powders, and that is what I need. That is what I need. Means I have least porosity because of the additional hydration products, and there is no continuity of the pores. You must be knowing the pore continuity is zero here. It's zero here. There are some discontinuous pores. There is no continuous pore. But you can see here there are a lot of continuous pores are existing. So that is the advantage when you add nanoparticles into the cementitious system. So means it complements the chemical reactions on cement surface. That's what is discovered or did by Thomas et al. Some of the people are writing like, you cannot hear my voice.
Yes, sir. Your voice is breaking in between, sir.
Okay.
That's
Yeah. So you can hear me now?
it is better now.
Okay. it is okay, or shall I log into my mobile? Okay, like, because now I am talking from my system. Is it okay, or shall I go into my mobile, log into another system and
Any participant may confirm whether the voice is okay now, may unmute yourself, and Dr. Hegde is also here. Any participant?
Sir, it is okay. It is audible.
It is okay.
thank you, thank you.
Okay.
Okay.
It's clear, but some low. If
Yeah, because simultaneously I am hearing, but it is for me, I feel it is sufficient. Okay, maybe I don't know, like, because I can understand how much I am speaking actually. I mean, what is the like volume of is going to this video. So I see it is fine. Like maybe some of you may be having some internet problem. So shall I continue?
Yeah, yes, sir. Yes, sir.
Yeah, yeah. So, so let us go to the Nano Silica, that is Nano SiO2. Now, you know, when I talk about the nanoparticles, there are varieties. There are many types of nanoparticles. But for us, for concrete technologists, for civil engineers, we know the Nano Silica, that is Nano SiO2 is the best actually. Is the best one, okay, because it is siliceous and I need a siliceous material. So first nano product that replaces the microsilica of the silica film is the nano SiO2. Now nano SiO2 composed of the silicon dioxide as the chief chemical constituent. We know we need silica because I have plenty of calcium with my cement. And particle size nanosilica varies from 5 to 650 nanometer, but with spherical morphology. Well, I was talking about when the nanoscience is between 1 to 100 nanometer, but it is difficult for us. Even using 100 nanometer size particles. So, researchers have used 200 nanometers, 300 nanometers, even they have gone up to 500 nanometers. But most of the morphology found to be spherical. Spherical, okay, morphology gives me the ideal, okay, ideal for my cementitious system or for my hydration. Or you can say, when we produce nanoparticles, the ideal is the spherical morphology. Okay. So, this flowchart talks about the influence of nano SiO2 on the concrete properties. Well, there are numerous advantages of nano SiO2. So, but I have just made a flowchart. Well, this presentation actually, this one is carried out by one of my PhD scholars. So I should say credit goes to her. So what we decided, let us divide, okay, the advantages of nanosilica into two parts. One is, we know this is a highly pozzolanic material. Highly pozzolanic material. I just showed you how it acted in the beginning itself as a calcium silicate hydrate sieve. So what happens actually, it consumes lime from cement reaction and improves early as well as final strength. That is most important, is it gives me the early strength as well as final strength. And also improves possibility for nanofiller. Well, when you talk about the nanofiller, come here, fill in the voids. So what is the fill in the voids? The dense packing. Dense packing. It expels water. Normally, what happens? Now, once you expel water, okay, from the hydration products, that water available for the molding and improve plasticity. Well, some point of time, it doesn't hold good, I will tell you, and we will discuss about that also. But dense packing helps me in the less porosity and resulting into the durability improvement. Okay, this part is not holding good actually. So now we will discuss about it. Now, yes. Now, the smaller particles in nanosilica, there are some weaknesses. What are the weakness? Weakness is induces drain shrinkage, autogenous shrinkage, thereby developing a large number of cracks in concrete. Now, what is my shrinkage? You know it very well. When I am going to add smaller, okay, to smaller particles, okay, smaller size fractions, shrinkage is going to be more and more. Now, what is the solution here? Well, solution here is the quality control practices. You have to adopt a better curing. You have to adopt a better quality control practices. That is the key here. And you know, many of the industries where with whom okay, we are working, with many of the ready-mix okay, concrete industries, this is one of the main reason okay, of non-adaptability. You have to really pay attention in the site, the excellent okay, quality control practice. If you are going with the smaller size batches and that too nano size batches. All right. So then I will talk about how it is giving problem okay, in the lab also in experience numerous. Now non-economical. Well, till now it is the economics is not okay satisfying. It is very, very costly. The production cost is very high. So we are not getting away economical because of also not much of a uses and construction industries is unable to afford it. Now, third is the high heat of hydration. Well, when in the beginning itself, when nanosilica is going to act as a calcium silicate hydrate seed, remember and understand the evolution of heat in the system. So you have to adapt, you have to divide a mechanism how you are going to accommodate the high heat of hydration. And that is what is basically okay, making my slum the workability challenging. Workability is the challenge. Well, we have experienced the slump loss, but it can be mitigated. Remember, this can be easily mitigated. We know the chemical admixtures at this point in time. It is basically a revolution actually. So if you deal okay with any of the admixture, particularly the super plasticizer, the slump loss can be minimized or can be handled easily, but not the height of hydration, neither the shrinkage. Well, we have also shrinkage compensating admixtures, but the cost is increasing. Well, whatever the case, you need an excellent quality control practice. Then, okay, definitely can be. Now, so what we realize, what is the need at this point of time? The need is use secondary cementitious materials in conjunction with nanosilica. There, you can produce a high performance and sustainable. How? Well, we know we are now replacing. Okay? Most of the cement companies now they are replacing fly ash minimum 25%. If you purchase Portland Pozolana cement from the market, definitely you are going to your cement will be having 25% of fly ash. Okay. Similarly, if you are going to purchase a Portland slag cement, minimum 30 to 40% will be the slag. So that is what is good for us actually. This is a good, okay, a very good initiative for us. Now, what is proposed here is, well, we can integrate some percentage of nanoparticles along with the secondary cementitious materials. Now, why? Well, we know we are producing the binary, like ternary or maybe quaternary. Well, you must have heard of like some research is going on adding fly ash, the GGBAs, okay, along with the office. So there are a lot of varieties going on actually. Now, the key here, remember the key here is when I am designating yes, 25% of my fly ash will be there in OPC. That is fine. But when I'm going with a more number of proportions, so I cannot go into a trial and error method. So I have to go with a understanding how I'm going to play with the materials, play with the combinations. So how I will do actually? Well, I have to do with the a concept for particle packing concept. A concept for the particle packing concept. So this concept is nothing new, I think. Is nothing new. We know it very well actually. So the packing density is the volume of solids divided by total volume. That is my Vs divided by Vs plus Vb. Okay, Vs plus Vb. Now this one we know from the soil mechanics. Everyone of us studied very well about the packing density, the characteristics of the packing density. Now, if you check, okay, what is the concepts of the packing density or the particle packing? Well, you can see here the three pictures are here. One is the first picture is a square having you can see the particle size of almost uniform. Isn't it? Almost uniform, single of it, grade actually. Now, what is happening here? Well, if you proportion of a single size particle, you will get so many number of pores. You can see the white one is the pores. What is second picture? Well, the second picture is what I did actually within the pores or it is the void spaces between the large particles. I just filled with smaller size particles. Okay, smaller size particles. You can see here the smaller size particles. Second space between the pores of larger particles. So what I'm doing actually? My density is increasing and my porosity also reducing down. Now in this picture, the third picture, what I'm doing again between these small particles, I can able to integrate still smaller size particles. Okay, still okay. The smaller to smaller size particles. Again, okay, I can increase my packing density as well as I can minimize the porosity. And that is what is the basic concept of particle packing models. Means the concept is try to increase the volume of solids by reducing the pores. That is your volume of void. Okay. Now, if you see based on this concept, well, there are a lot of actually research is being carried out. Now, particularly adapting these models or adapting this research into the practices is important at this point of time. You must be knowing when the soil scientists talk about the soil mechanics, they always talk about the density. Now, similarly, we have to integrate some of the models in the concrete technology or in the construction practices where it will define the models or it will integrate the models to which we can increase the packing density. Well, and this model, when we checked in the literature, it is started from 1980. Now, Dinger and Funk are the two researchers who spoke about in the beginning, okay, in 1980s, how this can be applied to the cement science, considering the minimum particle size distribution. In the entire distribution of the particle size, based on the minimum particle size, they proposed a model. Then slowly, like now, you can see there is a model and that is modified Anderson equation. Means Anderson taken that model further, then they kept on modifying, and then finally they came up with this equation CPFT, that is the cumulative percentage final, is depending on the all the sizes. Means minimum particle size, maximum particle size, also the average particle size in the system. Also, they have taken Q, that is which is nothing but a coefficient or exponent depending on the workability, the level of workability you are going to work. So they have included everything here actually in the modified version of the model. And that is what we have adopted, integrating nanoparticles with the cementitious system. Okay. Now, I just want to highlight here why there is a combination, why there is a necessity of combining the secondary cementitious materials with the nano silica. Well, we know secondary cementitious materials, when you use, there are numerous advantages, but there are also some disadvantages. Disadvantage, for example, particularly on the compressive strength of the cementitious system. One of the disadvantages is the early strength actually of the concrete or early strength of the cementitious system. Now, similarly, we know that Nano Silica, there are numerous advantages, but there are also some disadvantages. So, what they will do actually? So, what we tried, integrate both, and we expecting, it is very much essential to counterbalance each other. They will just adapt the disadvantages of each other, and they will give us a high performance sustainable cementitious composite. And what is there, it is really work, right? And we will talk about it. So moving to the experimental methodology, now these are the physical properties of OPC, fine aggregate, fly ash, and the ultrafine fly ash. Okay. And you can see here like all the materials like OPC, fine aggregate, ultrafine fly ash. And this is the properties, physical properties of the nano silica. Actually, Nano Silica we have procured from a lab in Mumbai, and they are the people who supplied continuously depending on our requirement. And this is the actually particle size we just restricted to 20 nanometer. The dispersion medium is water. Well, I was just talking about handling of nanoparticles is another issue. So how we handle? Not in a dry scale, we cannot handle it. It is very dangerous, fascinating. So we just gone from procuring the colloidal nanosilica, and the dispersion medium is water. And rather, when we did the mix design and all, so we deducted the water. The solid content is only 40%. Means the bottle is to come 1 liter bottle, suppose. So 400 grams will be on nanosilica. 600 gram will be the water. pH is very much alkaline. This is the viscosity. This is not much important actually. And this is the particle size distribution of all the materials, starting from the sand of it, because we work on the water, sand, and all the fly ash, ultrafine fly ash, then the cement, and then the nano. So this is what is the modified, or you can say the expanded, version of the particles distribution. You can see here like the nano silica is an extremely left actually, almost a single size, okay. And then ultra fine fly ash, also a single size particles, fly ash, then cement and the sand. Excuse me. Okay. Then experimental procedure like, then we adapted the particle packing by modified Anderson and Anderson model. We designed the mixed proportions or designed the water mixes and the cement test. Well, as I was telling you, like the mix recipe, okay, of the multi-blended motor mix is prepared using particle packing design tool, and that is nothing but EMA. There is a software which works on the principle of modified Anderson and Anderson model. So if you give an input, yes, these are my materials I'm going to mix in the mixed proportion, and these are the my sizes of the particles. Then depending on the maximum density, it will give you the proportion. Yes, this proportion is going to be the best of it. Proportion which will define the best packing density. So based on that, these are the like per meter requirement for this mixes. Now this is the designation of the system actually. Like we have gone for control, that is without any addition of the materials. Then the binary blend, then the binary blend is only OPC plus fly ash and OPC plus ultrafine fly ash. The ternary blend is OPC plus fly ash plus ultrafine fly ash. Then OPC plus fly ash plus Nano Silica plus OPC plus ultrafine fly ash plus Nano Silica. So you can see here OPC in a like binary and ternary blend fixed as 75%, and 25% is the total replacement, where okay the proportion, okay, like for example, if you go to the OPC fly ash Nano Silica, now this 25% is divided into 23% of fly ash and 2% of Nano Silica. So means we have OPC plus fly ash, which is 75-25, and OPC plus fly ash Nano Silica, that is 75 for 23 and 2. So that is what is the distribution. All right. So and here now M designates is the motor and P designates is the test. So because we have gone for some advanced characteristic studies, which I'm going to talk about today, there we did with the test. Now this is the procedure for the blended of specimens. This is for the motor. Now we adapted a motor-matic motor mix actually, and you know the standard size is 70.6, and for a RCPT test, it is a standard of a like size 100 mm and 50 mm, 100 mm diameter, 50 mm height. And once casting is over, they are compacted and stored in humid condition of a humid chamber, and then are demolded of 24 hours. Now, what the test we did actually, we did okay, from the motor, we did compressive strength, density, permeable porosity, and rapid fluoride and penetration test. Now you can see here, this is the procedure. Like this is my automatic motor mixer, and here the molds for the cube specimens, and this is the for the cylindrical mold for the acidity of the test. And these are the, you can see after demolding, they were kept in the container for curing, and then they were tested. Okay, for compressive strength, this is the compressive strength, and this is for rapid fluoride and penetration test. Okay. Then similarly, the preparation of the blended test specimens are also well done. Then mixing of blended cement motor through automatic motor mixer, and the only thing that there is a procedure of like the setup is different, and what are the measurement done actually? Measurement done for setting time, surface temperature variation, Then workability, chemical shrinkage, and also advanced characterization of the sample. That is what, okay, I'll talk about the hydration and microstructure. So basically we procure, okay, this is silicon mold, okay, mostly being used for preparing chocolates, mostly homemade chocolates and all. So we procure this. This is basically cylindrical, okay, silicon molds, okay. Diameter is upper dia 4 centimeter, lower is 2.5 centimeter, and height is 3.5 centimeter. Same condition of the followed, and they were kept of it during time for certain durations. Then once the attaining the certain duration, for example 7 days or 28 days, then their hydration stop actually through solvent exchange technique using isopropyl. Because we know for going for advanced hydration, we are not going to get a slot on the 28th day or maybe 56th day or maybe 7th day. So we have to stop hydration and to keep it in desiccator. So different desiccator, whenever we used to get a slot, we take the sample and we go for advanced hydration studies like XRD, you did XRD, you did TGA, and also we did SEM with energy dispersal spectroscopy. Now this is actually the pictures, setting time, surface temperature, workability, and chemical synthesis I told you. And these are the measurements. This is for the setting time, this is for the temperature. Okay, you must have seen, okay, widely now being used, okay, like this is infrared thermometer, and this is basically your measurement of workability, means how much flow is happening, and this beaker is designating, means or showing us the measurement of chemical synthesis. Okay. Now come to the thermogravimetric analysis. Well, as I told you, like going into the results, but let us, before going to the results, let us understand how we have done the thermogravimetry. Well, as I told you, samples were kept in desiccator, stopping the hydration. Then when the slot is available, or maybe, well, TGA, this equipment is in my lab, so we whatever actually we do this, but not all that equipment actually. So what we did actually, well, samples were heated to a temperature range of 50 to 900 degrees centigrade in the nitrogen per atmosphere at the heating rate of 10 degrees centigrade per minute and per rate of 20 millimeter per minute. That is basically the equipments, okay, will ask. So we are not, okay, we are not worry much about this part actually, but important here is what the temperature range the PG was done. That is important. You can do. Now, when I talk about on the basis of thermogravimetric results, now the calcium hydroxide. Now I know the calcium hydroxide content, the weight loss with the temperature is of 400 to 500 degrees centigrade. So remember, the resolution of calcium hydroxide happens within 400 to 500 degrees centigrade. So what I'm getting here, well, this equation is already given by Singh et al. A, Singh et al. B, okay, both of them, like they're giving how you can determine the calcium hydroxide content from TG thermogravimetric results. CaO plus H2O and CH percentage, you can determine the percentage of WCS divided mass of H2O. Okay, so that will you know. So percentage of like calcium hydroxide you can determine through this equation. Similarly, water associated to hydrogen product except calcium hydroxide content, also given by Sorry et al. Figure 13 of it. Now, what you can do actually, you can determine the total water is getting buffered, okay, and subtracted by water required for the calcium hydroxide. Water required for the calcium hydroxide. So now remember, water associated to hydrogen product. Now, as I told you, there are many hydrogen products. Okay, there are many hydrogen products. But primarily, okay, we have calcium hydroxide and calcium silicate hydride. So let us assume, okay, now even though we designate as a doublets, means that is water associated hydrogen product except CS, but dominantly, okay, this percentage is nothing but your calcium silicate hydride. Remember, so because we are subtracting of it, the calcium hydroxide, so mostly this will be dominated of it, means all can see the most of the part is the calcium silicate hydride. So we'll discuss about the results part. Then extra diffraction of it, like mineralogical studies of it was carried out through a XRT, that is without central research facility, and then it was characterized through the expert high score software. You must be knowing that there is software which easily okay, which makes out like easy in characterizing the peaks that we are getting through the Excel. Okay. Then some samples we did okay for the scanning electron microscopy powered by energy dispersion spectroscopy. That is also a central facility. Well, you know, like scanning electron microscopy is nothing but a image processing technique. So what you can get? You can study the morphology. You can study the surface morphology. Now, well, we can understand some of the things of the through morphology, but if you go for a quantification of the material or quantify the studies, then it has to be integrated with the physics. If you integrate PDX, then you can quantify the change in elemental composition within the boundary of the layers. So that is okay going to be given by the energy dispersion. So we'll discuss about that when you go to the results. Well, so from the results and discussion now, let me first go to the particle packing by modified conversion and understanding. Well, you can see here we have fitted. Now, why we did this exercise, even though using a software that is EMA, but we just made like or we ascertain like whatever the proportion that we are getting should be close to the ideal curve. Well, you can see here, this is the black line is the basically the ideal curve that will generate when you given the particle sizes in the EMA software. Now, your all the graphs, remember, should be close to the ideal curve. That is what is the optimization. Optimization. So if you keep on doing okay with the curve, with the proportions, or it will designate a proportion okay, that has to satisfy, it is fitting very much closely. So as per the like my actual gradation curve, all the mix on to 50 with the ideal gradation curve with a Q value of 0.3. Q is the basically is the medium of it. Point reaching is the medium range of water. So we just checked okay whether it is like fitting properly, fitting suitably or not. So we did some statistical of it, just fit, and this okay, you can see all the mixes are very much close. Definitely cannot be ideal, but they are very much close. Most of it, they are all are close to the almost close to 0.9. Now here, now the see you can see here this is a fly ash mix, this is ultra fine fly ash, this is a fly ash ultra fine fly ash, this is a fly ash with nanoparticles, this is ultra fine fly ash with nanoparticles. Well, you can see the more and more okay, you are going with the finer particles replacement, you are getting a better actually R square. Why? Because I am getting a better packing. Because my cement is already in the micron size. And if you are adding another, now fly ash is also in micron size, we know it very well. Suppose if you add micron size to another micron size particle, Well, for a hydration point of view, it's absolutely fine. But for a packing point of view, it is showing a value, okay, fine, this is close to 0.9. But here you can see the same proportion, displacement is same, 25. But what I did actually, flyers, I restricted 23 and 2% I add nanoparticles. Now you can see the improvement here is 0.952. So means the software, okay, understood there are there are multi, okay, level of sizes in the cementitious system, and that will add value to the particle packing. So the concept is, as I showed you one of the picture of it, like the gaps between the larger particles filled by the smaller particles. Again, the gap between smaller particles filled by the further smaller particles. So that is what, okay, we are getting, okay, here we are to the practice, right? Whatever the conceptual is we are talking about, but actually we are getting in the practice also. So similarly, the ultrafine, okay, and the ultrafine nanoparticles. Here it was 0.89, and you can see the ultrafine nanoparticles 0.972. That is the, okay, beauty. Means here cement, which is some micron size particles, ultrafine flyers is a some micron size particles, and nanoparticles is 10 to minus 9, still small. So there are three varieties of particle size we are mixing, and that's why you can see it is giving me the best of it for you. All right. Now this is my compressive strength. Okay, like so just for understanding, like I'm just given you, but what the advantage here is at the early age, 3 and 7 days, you can see the results 3 and 7 days, like flyers, ultrafine flyers. Even the flyers ultrafine mixes having lower compressive than the control motor. We know it very well. We know it very well actually when I am going with it. Secondary cementitious material, I have to compensate for the early age compressive strength. Now come to the ternary blended motor. That is particularly if you come to the nanoparticles, in like these flyers nanoparticles, ultrafine flash nanoparticles, you can see here the even 3 and 7 days, the intensified compressive strength at the early age, 3 days only increased by 10% and 18% respectively. So that is the beauty of the adding even a very small percentage of nanoparticles. So what is the actually what is the reason? Well, reason I have already told you, and again I'm telling you the nucleus site for the calcium silicate hydrate gel formation, and also the pozzolanic reactivity, high pozzolanic reactivity, and the calcium silicate hydrate seeds, and that is what is the nucleus site. Okay. Then your density and permeable porosity. Well, it is fine. Okay, you know the density is like green line. You can see here is the ultrafine flyers and nanoparticles, and in the particle packing concept, also we have got the best fit actually. So ideally, this will give you the highest density, and more density. You can see here the porosity is the lowest among all the mixed. All the mixed. So that is what, okay, from the particle packing concept, like the when I did the statistical fit, I was very much sure the density and porosity is going to be the best. Next is your rapid fluoride and penetration test. Well, here you can see, okay, like all of our mixes except control motor, okay, but control motor in the early age, okay, 3 days, it was around 1,000, more than 1,000, but the moment the age prolonged. The design mix was only for motor. Okay, so the porosity will be very much less definitely. So the charge pass kept on reducing, but you can see the green line is showing the lowest. Green line showing the lowest. So now in the 56 days, okay, the comparison is showing percentage reduction in charge pass for fly ash, 25 ultrafine fly ash, like fly ash ultrafine and fly ash nanoparticles and ultrafine fly ash nanoparticles. See the okay, how much of it they are getting advantage. The as compared to control, that ultrafine fly ash nanoparticle mix is getting 70% of a reduction in the charge cost. So that is what is advantage of packing density. Remember, this characteristics is going to help you in a long run. This is going to help you attaining a durable mix, attaining sustainability point of view. They may not, like they contributed significantly in the composite system, but they are more pronounced, particularly in the durability, particularly in the impermeability. So that is what actually is important for us at this point of time. The setting time also setting time is basically the control motor, okay, and we know that when we go with the second cementitious motor material, ideally, okay, because of the slow pozzolanic reactions, the time will increase, isn't it? That is natural actually. But when you slightly nanoparticles, slightly, when you add 2% only nanoparticles, and they are almost matching it with the control. Means there is no delay in the setting times. They are almost actually matching. So I have mentioned here the binary blended fly ash mix, which is increase the initial final setting time compared to control. This may be attributed to slow initial pozzolanic reaction of fly ash particles. As I told you, okay, same thing I told you actually, and we know it very well. Now come to the same thing here also. Now when you come to the Nano Silica, that is accelerated setting time, that is reduction in the dormant period, faster rate of pozzolanic activity and hydration by Nano Silica. That is what is happening, okay, when I am adding nanoparticles. And this is my surface temperature. This is very, very important. Actually, we measure through an infrared thermometer. Well, and all the tests actually we did in the only morning session. In the morning session, because Suratkal is which is Mangalore city, part of Mangalore city, like is basically on the Arabian Sea coast, just on the coast of Arabian Sea. Now, what is the problem here is we have a lot of humidity. And our institute is on the coast. We have our own private beach. You can imagine, okay, just on the coast, just on the sea. So the significant change I have experienced as the day passes. So I made ensure like all the tests should be done in the morning of the day, that is only between morning 8 a.m. to 10 a.m. Well, it was you can say that point of view, it is controlled, but again, if you see, like we just measured a thermometer from a distance, okay, from some centimeter of a distance. Actually, that part was not counted. Now, let us see the pattern of rising surface temperature. Now, you can see the control, the peak temperature is 32 degrees centigrade. Peak temperature, the control is 32 degrees centigrade. Now, when I'm going with the fly ash, ultrafine fly ash, even the fly ash and ultrafine fly ash, they are tremendously okay. The surface temperature reduced. The peak temperature of the surface reduced actually. So imagine that with the peak temperature is this much, 32 degree for control. Imagine the temperature of it would have been happening in the core. And so that's why you know, whenever we go with the mass constructions, fly ash is one of the key ingredients because it lowers the temperature significantly. Now, again, the problem is like when I'm adding nanoparticles, when you at a smaller scale, very, very smaller scale, you can see the temperature is rising again. Means they are almost getting close to the control motor. And that too in the surface. Well, we are just we were about to measure made a device to understand what is happening to the core temperature for a nano silica admixed cementitious composite. But by the time, for last 1.5 years, we are completely dumb actually. Like, there's nothing like labs are closed. You know how much of a time is going with the COVID. So so that's why I don't have the measurement of the core temperature. So I am sure this nanoparticle admixed cementitious composite, the core temperature will be much more even than the control. I am very much sure. And we will measure it at some point of time, and if situation like improves, and I may be in a position to like tell you what is the core temperature of the nano silica admixed in this form. So that is what is a disadvantage. Means that is what is asking the engineer in charge, the sites, go for a best quality control practices. Go for a best curing systems. That is the need. Why actually we know it very well. Faster hydration reaction and increased nanosilica in conjunction with fire outer fine surface temperature was found to increase approximately 90%. That's what I was talking about. Then workability, well, workability is like I will tell you like workability. As compared to control, we know the fly ash and ultrafine like they will increase the workability. But when we started using nanoparticles, well, we could not do it. I'll tell you, like these are the like flow values we have matched by adding a superflux that to polycarboxylic ether base. That is necessary. You cannot work with nanoparticles without having a superflux. Well, here the percentage was very, very less. That is 2%. So we didn't require of using it for practice hazard, but the moment it is going to 3%, we have seen it is impossible to work without a super practice hazard for a nanoparticle, nano silica or admixed cementitious compound. So this is basically your workability, and this is your chemical synthetase. Now let us go one by one. Like fly ash 25, lesser change in volume compared to all mixes. Insignificant hydration activity during first few days means for a fly ash mixes, the volume stability is much better actually. Means what is saying lesser change in volume means the shrinkage is going to be minimized. There may not be any kind of problem in the size of shrinkage. That is understood. Now, when you go with the ultrafine fly ash and fly ash ultrafine, then there are induced volume change, which could be due to fine filament faster reactivity. Again, when I'm going to nanoparticles, the moment I introduce the nanoparticles or nano-SiO2, higher rate of chemical shrinkage as compared to control and other. Now the question is, you can see here now, well, this you can see there is a line, the top line is basically the ultrafine fly ash and nanoparticles. Now, you must have seen, you must be seeing, okay, after 14 days of the measurement, beyond data is not there. But this one is my fly ash and nanoparticles. This data is there up to 56 days. But this is not there. Why? Because the sinkage was too much. The volume stability, the volume instability is too much. The measurement could not be done. And I am going to show you that in concrete science is we call as self-desiccation. That is leading to cracking and even further. So you can see here, this is the chemical sink and polar specimens. The specimen, okay, particularly for the ultrafine fly ash nanoparticles, because it contains only the ultrafine like particles, submicron size particles. You can see, okay, the beaker is getting broken. So one of the day we realized, like 16th or 17th day, or I think 20th day, we realized the beaker, there is all of it leakage of water, and because of the self-desiccation, there is a crack developed in the beaker. Okay, so that is what is the basically your sinkings. So that indicates we have to go with the a significant of quality control practices. It is very much essential. All right. Now let us move to the thermogravity analysis. That is moving to the advanced hydrogen studies. Now if you go to the literature of thermogravimetric analysis, like of the results, like you will see most of the people will talk about there are 3 different phases in a cementitious system. Like 110 to 400, that is dehydration of water molecules associated to calcium silicate hydrate. 400 to 500, dehydroxylation of calcium hydroxide. 600 to 800 degree, decarbonation of calcium carbonate. So this is what you have to understand is happening, okay, when we carry or when you do, okay, thermogravimetric analysis. Now, if you see a thermogravimetric analysis plot, well, this is my thermo 3GA plot. This is my TGA, and you can see the peaks is my DTG, that is differential thermogravimetry. Now, this is my TGA, that is thermogravimetric, or you can say TG percentage is presented in the left side, and the DTG percentage for grams is presented in the right axis. Well, left axis, what will it show? It will show the percentage mass flow. Percentage mass flow means, suppose any sample if you take from here 100 percentage, okay, what is the percentage? Okay, it is getting lost at 900 degrees centigrade. That's what you can understand. That is the basically your stability, okay. All right. Now, when you go to the DTG, now DTG is just this graph. What it is, well, DTG will show there are different phases. Now there are different phases actually, and the loss of water happen in different phases, or you can say different temperature boundaries. What are the temperature boundaries? These are the 3 temperature boundaries. Well, the first temperature boundaries we know is 110 to 400 centigrade. Well, there will be many actually. Okay, you can see, but you can see here it is starting little early. That is fine, but we know the mass loss is happening between 110 to 400 is meaningful to me, because it will designate with respect to the calcium silicate hydrate. So what I have to do, I have to consider only this zone if I want to know about calcium silicate hydride. Similarly, we know the 400 to 500 degree centigrade is calcium hydroxide. So I have to adopt only this zone. Similarly, the calcium carbonate, well, calcium carbonate is not part of this study actually, but those who work on the carbonation process, they have to hold this zone, that is 600 to 800 degrees centigrade. There you can understand the decarbonation of calcium carbonate. So based on this, and if you put into those equations I told you before in the experimental methodology, you can get the amount of calculated CH. Amount of calculated CH. Now this is the percentage. You can see the control to nanoparticles of all the mixes, and this is my percentage of calcium hydroxide. Now what is the observation here? Well, the observation here is, this is my control. Now 7 days data is in the blue and 28 days in the brown color actually. Now let us go to the 20 days. 20 days. Okay. 20 days. Percentage of calcium hydroxide to compare with the control motor. Flyers reducing, all are reducing actually. Now if you compare with the control, with the flyers mixes and the nanoparticle mixes, there is a drastic reduction in the calcium hydroxide. Well, we know that calcium hydroxide is responsible for the permeable porosity. Remember, your permeability is dependent on the how much percentage of calcium hydroxide is generating in the hydrogen process. So what is happening here? Well, this is percentage of calcium hydroxide is drastically reducing by adding a very small percentage of nanoparticles. Okay, give me just a minute. I'll just call you. Where is the presentation? So you can see here, like means by infusing a very small percentage nanoparticles in cementitious matrix, I can able to drastically reduce the percentage of calcium hydroxide and thereby strengthening the system, strengthening the cementitious composition. Okay, now come to the amount of calculated doublet. Doublet is, when I explained to you, that is percentage of hydrated water except the CH. And I was telling you, most of the hydration products, if you deduct CH, mostly it will be the calcium silicate hydrate. But we cannot designate it only CSH, remember. That's why, okay, we designate as a doublets. Now, similarly, well, this is the reverse phenomenon. This one, you can see here, we are getting the moment you are adding nanoparticles, we are getting, as compared to the control, even the flyers mixes, we are getting additional calcium silicate hydrates, and that is going to benefit for me. That is going to bonus for me. So whatever I spoke actually, like binary and ternary banded flyers, outer flyers, no much impact on percentage of calcium hydroxide and percent doublets was observed at early age of 7 days. However, slight improvement is noticed in presence of ultra 0.5 years. But integral nano silica and ternary banded mixes found to be a significant progress in hydration activity, indicating that intensified reduction in percentage of calcium hydroxide. Pronounced growth in doublets percentages compared to that of control. Okay, that is basically the technical language, but I explained you very normally. Now the mineralogical characterization. Let us go into the mineralogical characterization. Well, you know this is the graph from the X at D. This is my contour. This is my fly ash, ultrafine fly ash. And come here, this is my nanoparticles, okay, admixed. Now compare the graphs. You can see count the peaks. You can see the peaks, how the peaks are increasing from control to fly ash to ultrafine fly ash, like slowly. The moment you come to the nanoparticles, you can see the peaks. Means you are getting additional peaks. Now, what are these additional peaks, or if it's the prominent peaks? This prominent peaks is calcium hydrate, found to be in the form of tobermorite, and calcium hydroxide in the form of portlandite. So, what is happening actually? Presence of nanosilica in both fly ash nanoparticles and ultrafine fly ash nanoparticle samples amplify the peak of CSH and dramatically reduce the peak of CH. However, among the FN and UN samples, UN showed a higher intensity of CS and lower CH. That is fine. But remember, the moment I am going to nanoparticles, I tobermorite peak, that is basically your gel. Okay, that is basically your gel. That is found to be very much intensified. Okay, and that intensify. You can see because this picture is very much of actually more. You might have to see it actually, but we have identified the symbols and which symbol, okay, designates to what. Like for example, this symbol is CSH, this one is SiO2, beta is calcium silicate, Q is for quartz, Psi is for calcite, theta is for vetrite. So like that, okay. So there is okay a designation of it is defining the peaks. Then come move to the microstructure analysis. Well, microstructure analysis is carried out okay through the calorimetric microscope. And as I mentioned you, we can understand the surface morphology. Well, you can see here, this is my contour. This is my fly ash. This is my ultrafine fly ash. This is my fly ash ultrafine fly ash. These are both are my nanoparticle admixed mixes. Well, if you keep on observing the contrast is changing. Okay, now slightly okay, brighter towards the slightly okay, darker okay, images. That indicates the density is increasing. That means you are having a dense microstructure when you are adding a nanoparticles in the cement system. Well, here you don't have a dense microstructure. You can see here the fly ash, lot of appendices, lot of wires. So that is indicating a loose microstructure. So that's what okay is, but we cannot really quantify. This is basically our morphological observations. Because this is being done in a secondary electron mode, it will just give me a surface morphology. But what I will do actually, if you really want to go into the quantification studies, now remember you have to integrate your SEM with EDX. Now EDX is going to define the elemental analysis. Now, based on the elemental analysis, what we did actually, we just okay determine the calcium to silica ratio. Well, calcium is an ion and silica is another ion. We know the both ions for a cementitious composite is very much important. Now, what we did actually, let us compare the atomic ratio of calcium by silica. Now, how did it actually? Well, now you must have seen this is the image. Okay, this is the image, and I have to define a boundary when I integrate EDX. So I have to define boundary. Now you can see this boundary is from this boundary I am getting this peaks. So these peaks are basically the elemental peaks, and this table gives me the quantification of the elements. So now you can see here calcium 32.27, silica 12.9. So what is important for me? Oxygen also there, magnesium, everything is there. But for me, important is the calcium divided by silica. Now what it will define? It will define or it will analyze the chemistry of CSH solid formation in the matrix of hydrated cement paste. In the matrix of hydrated cement paste. Now what is this? How you can characterize? For example, a lower value of CA by SI ratio characterizes the compact and densified microstructure of cement matrix due to the development of stronger network of CH by means of CH conjunction. So remember, the CA is showing less, means that is like the most of the CA is consumed, okay, with the silica particles, and they or maybe the calcium hydroxide is reacted with the silica and form the calcium hydroxide, and that is actually its characterized. Okay. Now this is actually table for CA by SI atomic ratio for a blended cement, and you can see here this is my control, this is my binary plants, and this is my ternary plants. Let us take an example for 28 days. 28 days, now you can see for ternary blends, even 25P, it is showing 1.346. Same, okay, you see the control, which is 2.186, is quite high. Okay, quite high. So that designates this mix has more formation of calcium silicate hydrates, and that is why it is forming a dense microstructure. And we have seen, and this is a kind of a validation of additional validation of what are the conventional, okay, like measurements that we did, compressive strength, density, the permeable porosity, all this. So reduced value of CA ratio for all the cement samples incorporated with various combination of fly ash, outer fine fly ash, nano silica component of counter-best means. Whatever the case it is, at this point of time, don't go for control tests or control cementitious model or a OPC based. Remember, this is very important. Even though you cannot afford nanoparticles, cannot done mix, but go for binary bonds. That is essential at this point of time. Lower value, the reduction of CA by SI is due to the accelerated reactivity of silica and the additional formation of calcium silicate. Okay. So moving to the conclusion, now implementing the theory of particle packing modified or Anderson model, the right proportion of admixtures could be proportional for the production of multi-blended cement paste and water. Well, you cannot believe, initially we were thinking we have had 5% of nanoparticles, and the cost would have been significant if we would have decided 5%. Later we realized 2% is giving me the optimum density. So means it has saved tremendous amount of money for me. So right proportion of admixtures is very much important, and you can really adapt it to the particle packing process. Then earliest properties like setting time, surface temperature, and flow properties were tailored with a combination of microcytes, secondary cementitious materials, and nanosilica. Well, I am telling you, you can really manipulate the properties. You can tailor the properties how the way you want by adding suitable combinations, by choosing the suitable combinations. So this combination of SEM and nanosilica is really did wonder. From the TGA, the presence of supplementary cementitious materials with nanosilica combination showed the potential reduction in the calcium hydroxide amount and improvement in the WH quantity. Well, alone bias is fine, but if you are adding a small percentage of nanoparticles or some microparticles, that is changing the dimension of the hydration behavior, changing the dimension in the microstructure characteristics. Now, particularly the panel samples in presence of nanosilica had an immense effect in CSS and CH3, but additional calcium-hydrated peaks are much stronger after 28 days. This is the way from the HRB we got. Then CA by SA atomic ratio attained from the results of SEM index was found to be lower for panel bending nanosilica admixed samples at all the edges, indicating a denser formation of calcium silicate hydrate. We discussed about all these. So make ensure, okay, like you are producing a low CA by SI atomic, and that is going to make your system much denser, much better from the durability. So these are the references. Actually, these are the only two publications I'm showing you here, but there are many publications actually from this research. Also, this scholar has published numerously this particular concept. Let me see, what around 10 publications. But these are two important publications and very recent publications. One is from Construction Building Materials, one is from the Journal of Materials Engineering. So, if you want to go into the more, particularly whatever the presentation I have given, okay, limited to the primary blended motor. Actually, we have gone up to quaternary blended motor also. If you want to understand, okay, like know more, okay, data about understanding about this quaternary, okay, blended motor, you can refer this papers, and anytime you feel anything to discuss, you can, okay, really shoot a mail to me, and I'm ready to, okay, answer your questions. I think I deleted the references. So thank you so much. With a small, okay, like however we save our buildings, there are of a building setbacks, and cracks in concrete are just reminder that you fall apart, no matter how strong you are. So remember, this is more important actually. Now the crack, how we have to minimize as much as possible. Whether it is also shrinkage crack, but don't ignore. It will prove you are incapable. So with this, so thank you so much. Okay, thank you one and all. And if I think I finished just okay, I think 20 minutes ahead, just to okay, like you if you have any kind of queries or anything discussion, I will be happy to, okay, answer. Over to Professor Praveen Kumar.
Yes, yes, any participant can unmute self or herself and ask any query or questions directly with the honored speaker. Participants having one participant is asking, the nano silica is also known as admixture. If admixture is required for high performance concrete, which admixture can be used? Khatti, may ask directly by unmuting yourself, Jitendra Khatti ji.
Sir, can you read once again, sir?
Jitendra has written that the nano silica, also known as admixture.
Okay.
If admixture is required for HPC, which admixture can be used?
Okay. Yeah. See, I think Mr. Jitendra, you have raised a very good topic actually. Nano silica is, yes, okay, it is an admixture, okay. But what level of performance you are requiring is the important. Well, remember when we talk about high performance concrete, and we are being talking about high performance concrete quite a long time without using the nanoparticles. Without using the nanoparticles, we have used the micron size particles, like all kind of secondary cementitious materials, along with the silica fume, actually. Thereby, we are defining the high performance, actually. We are defining high performance. Now, what I am talking about is nano silica is a one more dimension of it is lesser than the silica fume. So, if you're talking about the ultra performance, and if you can do it, and if you can handle it, well, nano silica is going to be the best one. Definitely going to be the best. But as I mentioned you, if you go and talk to most of the ready-mix concrete, like I have spoken to many of the people actually, they are not ready to adapt it right now because of the handling issues and the high cost. If you can afford it, if it is like affordable to you, well, it is going to be the best one. It is going to be the best one actually. So judiciously, how you are choosing is important. Well, we have chosen judiciously the packing concepts. So what we did actually, we just choose combination of the nano silica with other materials. Well, we can go ahead with this one also. That's absolutely fine. So now it is very difficult to mention a single name. Yes, this can be used for high performance concrete. There are wide scale like which will give you the high performance. So I hope that is yeah.
So another participant has raised, of course, a common query,
Yeah.
from where we can get nanomaterials.
Okay, see, actually, as I mentioned to you, like we have procured from one of the lab in Mumbai. So there are many like people like in the country, they are actually selling nanoparticles of different dimensions. As I mentioned to you, our the nanoparticle that we have used is 20 nanometer size. Well, if you go into the dimension, depending on the dimension, the cost of the nanoparticles you have to pay. So if you go to the more lower and lower, you pay more. So there are numerous layers numerous number of companies are there which are selling nanoparticles. Even like many of the our CSR labs and all also they are claiming they are providing much of a lesser of a cost. But we have not till now got it even though we requested, but we have not got particles which are of low cost. That's why I would say if you are going to depend on the other private labs, I can give you some names, even the one from which we procure. I can definitely give it to you.
Since there are no further queries, participants, the second call, if any query or if any questions be asked.
Well, I will be happy to answer you, even though if you don't hesitate, and I will be happy whatever you ask.
It is so nice of you. Professor Das has explained intricacies of cement hydration, microstructure, which is a complex subject, but very nicely, very thoroughly. He has referred again and again particle packing, Anderson model, which are basic things to learn. And I am very grateful that he included these basic aspects of particle packing and enlightened all the participants, rather motivated to do research in this area, and he shared his research results also with us. So microstructure, he nicely explained. Rather, it is my favorite subject, as of you are aware, and I also heard in very keenly and got some new insights. So I am very grateful to Professor Das sir. And this, if there are no questions, as so many participants are writing that it is very informative, very inspiring session. So on behalf of all the participants and my own behalf and my Rajasthan Technical University behalf, I thank you so much, sir. And with this, I request your permission to this today's session.
Thank you so much. Thank you so much, sir. It is my pleasure. Actually, I just okay. And
சரி சார்
you have really given a good time.
One participant.
Yeah.
சொல்லுங்க சார்
Yes, madam. If you wish to ask anything, Akila, madam.
பண்ண முடியாதா நீங்க இது சொல்லுங்க சார் எஸ் பேங்க் சொல்லுங்க சார்
Yes, yes, we are listening you. We are listening you.
1,44,000 வருது 1,44,000 வருது சீப்பா சொன்னாங்க மேம் இது எஸ் பேங்க் 15 rupees சொன்னீங்க இல்ல சார் இப்போ எவ்வளவு போயிட்டு இருக்கு இல்ல லாஸ்ட்ல போதா
May I request you to write the question on the
ஏதோ
chat box
1000 குள்ள ஏதோ ஒன்று வாங்கி வைக்கிற மாதிரி சொல்லுங்க சார் பொறுமையா டெவலப் பண்ண பரவாயில்ல ஒரு 1000 குள்ள இப்போதைக்கு சேலரி வந்தா ஏதாவது வாங்கலாம் சார்
May I request you to write a question on the chat if there is any question, because your voice is not clear to us, and rather we are unable to understand what you are asking.
I think madam is speaking in some different language.
Yes, sir. Yes, sir. Yes, sir.
And this is okay. This is talking of some different aspect what I feel, because
So with this, we request to close.
Sir, thank
We
you,
propose
thank
to
you.
close this session.
Thank you so much, sir.
Thank
Okay,
you,
thank
sir.
you so much, okay, for inviting me to this okay.
Thank you.
Session.
Thank you, sir. Thank you.
Yes, sir.
Thank you so much, sir.
See you, sir. Okay. Have a good day. Bye.
And we thank all the participants also to be with us. It was a marathon session, so thank you all. I close this session with your permission, Das sir.
Yes, sir. Please. Go ahead, sir.